Do you struggle with concentration? Have you ever thought of your brain health long term? Bowmar Nutrition is revolutionizing the nootropic and cognitive health industry with Sharp Nootropic Powder and patent-pending Bright Daily Capsules, powered by NeuroBloom. If you struggle with focusing, think of Sharp as brain food that supports concentration. Sharp works with your natural brain chemistry to provide a heightened sense of well-being that can delay cognitive decline and also increase mood. Bowmar Sharp tastes amazing and comes in many different flavors, available in caffeinated and non-caffeinated versions. While Sharp is a short-term aid in cognitive health, think of Bright Daily Capsules as a way to improve overall brain health and prevent cognitive decline long-term. As we age, so does our brain. Supplementing with Bright has the potential to delay this aging process and helps your brain function optimally. Stay ahead of the curve and order yours today at bowmarnutrition.com and save $5 off with code GENIUS5.
Forget frequently asked questions,
common sense, common knowledge, or Google.
How about advice from a real genius? 95% of people in any profession are good enough to be qualified and licensed. 5%
go above and beyond.
They become very good at what they do, but only
0.1%
are real geniuses. Richard Jacobs has made it his life's mission to find them for you. He hunts down and interviews geniuses in every field: sleep science, cancer, stem cells, ketogenic diets, and more. Here come the geniuses. This is the Finding Genius Podcast
with Richard Jacobs.
Hello, this is Richard Jacobs with the Finding Genius Podcast, now part of the Finding Genius Foundation. I have Chris Polly. He's a project manager of the Muon G2 project at Fermilab. So we're going to talk about what this means for physics. So Chris, thanks for coming.
Hi, Rich. Thanks for inviting me. I'm happy to come out and tell you a little bit about the science we do.
Yeah, for people that don't know, what kind of activities go on at Fermilab in general, and then how does this project interface with that?
Yeah. Let me say a few words about Fermilab first. So I'm a scientist. Fermilab is one of the Department of Energy national laboratories in the country. Fermilab is unique amongst the national laboratories, and you can kind of get a sense of that just from sort of the mission statement of the lab. The mission statement of the lab is really to study, physics at its most fundamental level, to understand, space, time, energy, and matter, and the most basic principles behind the forces that govern all the interactions amongst the particles. So it's really cool. It's a mission statement that's almost as cool to go where no one has gone before. And in some sense, that's actually what we're doing with the science frontiers that we're pushing at the laboratory. Yeah, so just to give you a sense of what that means and what kind of science we do generally at the laboratory, we're really out to kind of answer the big picture questions of, our existence, our place here in the universe, and how the universe works at its most fundamental level. In that sense, I think we appeal to the nature of all humankind, where we really, would like to understand what is this miraculous place we live in, and how does it work? And so some of the big questions that we like to study, just to give you some examples, when we look out in the universe, we see lots of matter, lots of galaxies made out of matter, but for some reason we don't see any antimatter in the universe. That's very puzzling to us, because those of us that study the fundamental interactions at their most basic level know that the physics behind matter and antimatter is very similar. And so, we can look out in the universe, we can see the cosmic microwave background, the evidence that the universe started from a big bang, but we don't really understand, as the universe evolved, what happened to that antimatter. So we design experiments to try and understand that. For instance,
Well, quick question. How do we know that there was significant antimatter? Did it have to be in order for the model to work in the beginning?
Yeah, because, we think, in the Big Bang, we know that a huge amount of energy was created, and then that energy is converted into mass. And we know through things like Einstein's E equals mc squared, that the energy turns into matter. When we do those experiments in the laboratory, we find basically equal parts of matter and antimatter are produced. There's some small imbalances, but not enough to really account for the fact that we don't look out and we see any matter in the universe. But, that's just one of the big questions. I'm just trying to give you a feel, so overall, for the kind of things we do. We also, in our astrophysics group, we look out and we try to understand the acceleration of the universe. There used to be a question 20 years ago about whether the universe was eventually going to stop expanding and then gravity would pull it all back together into a big crunch. Well, as our scientific instruments got sharp enough, we were very surprised to find that the universe is not just expanding, it's accelerating in the way it's expanding. And whenever there's an acceleration, there has to be some kind of force, based on F equals ma and basic understanding of how acceleration works. And so that's called the dark energy. And we don't really understand what is the source of the dark energy that seems to be blowing the universe apart. So at Fermilab, we do all sorts of experiments. We do deep underground experiments where we build very sensitive detectors. We build telescopes that we put on top of mountains. And of course, at our heart, we are an accelerator laboratory. We're Fermi National Accelerator Laboratory. We're the home of the high energy physics program in the United States, and we're the stewards of the development of accelerator technology. And so a lot of what we do are experiments where we just do them terrestrially, making sources of these fundamental particles to really understand how they interact, and if we've really found all of them that are out there to find. So that's
okay. So what is the Muon G2 project about?
So the Muon G-2 experiment, that's what I work on, and it's one of these accelerator based experiments where we accelerate standard particles. In our case, we use protons that we get from a bottle of hydrogen gas. You strip off an electron, and then you just have a bare proton. We accelerate those protons to extremely high energies. We smash them into targets. And then on those targets, we make more exotic particles that once they're made, might only live from a few billionths to a few millionths of a second. And that's why you need an accelerator to study them, because you can't just go out and scoop up a clump of dirt, and find these particles inside the clump of dirt, because they will have decayed and gone away and converted back into more standard stable particles. So in particular, the particle that we study is called the muon. That's why we call the experiment Muon G-2, and I'll get to the rest of it in a bit. And muons, you can kind of think of them as electrons. They're very similar. They have the same electric charge. They have the same kind of spin properties. We now know these fundamental particles in many ways behave as though they're little spinning tops, which is, of course, kind of a mind-boggling concept because we also believe them to be point particles. So what does it mean to have spin and mass and all those properties when you actually, don't think you have anything, any radius. But the muons, as I said, they're very similar to electrons, but they're also different in some very important ways. So first of all, they're about 200 times heavier. And that's important because the physics we use them to study is more likely to interact with a more massive particle. And so although muons don't live very long, they're more advantaged to use for the type of physics that we study than electrons, which are stable, because, they do have this ability to interact more with heavier particles. And so the muons, the way they differ, so as I said, they're 200 times heavier. They're also unstable. So once you make one, they only live for about 2 millionths of a second. So you don't get very long to work with them. When they disappear, they immediately blink out of existence, and in their place appears an ordinary electron, just like an electron you'd find circulating around an atom, and 2 neutrinos are emitted, and the neutrinos go propagating out through the universe to rarely ever interact again. And, it's not like the muon is made of an electron and 2 neutrinos. Again, when it spontaneously disappears and it suddenly, in its place, these 3 other particles appear. So the thing we're particularly interested in with the muon is precisely determining its magnetic moment. Just to give you an idea of what the magnetic moment is, the most common way people think of magnetic moments is if you think about having a loop of wire where you have current circulating in the wire. If you take that loop of wire and you put it inside a magnetic field, that loop of wire will feel a torque. It will want to, align itself where the loop is sort of perpendicular to the direction of the magnetic field that it's in. This is, of course, the principle behind how we generate electricity. Except in that case, we build coils of wire and then we rotate magnets, or we rotate the wires themselves to generate electrical current. That's how turbines and windmills, dams, and fossil fuel powered turbines all work basically on that principle. So that's what the magnetic moment is. It's fundamentally sort of the way charge and current interact with magnetic fields. Now, the reason magnetic moments are particularly interesting for these fundamental particles, like the muon, the muon has an electric charge. And it has this spin property that we say makes it kind of like a spinning top. And so you can think of, if you have charge in a spinning object, that's kind of like having a loop of electrical current. And that means these particles have an intrinsic magnetic moment to them. Just as they are traveling along through space and time, they have an intrinsic property, just like they have mass and they have charge. They also have spin and they have a magnetic moment. Now, magnetic moments have been kind of when it comes to particle physics, have been an interesting thing to study for quite some time. And let me just give you a historical example that's easy to understand why magnetic moments are so cool. If you were a physicist around the turn of the 20th century, and you were starting to really understand the world, the periodic table, you understood there were these electrons, and you were to try and predict what you think the magnetic moment of the electron would be, you would find, I need to step back first and explain the other part.
Okay.
So in the title of the experiment, muon G-2, that G-2, G is just a number. And and it's a number that is proportional to how strong the muon's magnetic moment is. It's a kind of a factor we just defined out front to be able to talk about how strong the internal magnetic moment is of an electron or a muon or a fundamental particle. And so, interesting thing, back to the story at the turn of the last century, is that if you were trying to predict what G should be for the muon, what its magnetic moment ought to be, you would predict as a classical physicist that G should be 1. But with the advent of relativity and the understanding of quantum electrodynamics and the development of Dirac's famous equation, the prediction changed from being an expectation that G should be 1 to the expectation that G should be 2. And so in some sense, that's one of the ways we know that relativity and quantum electrodynamics are correct, and that's how the universe works, because you would grossly mispredict something like the G factor of an electron if you didn't add those components of the theory. And so, as you might already be able to guess, we name our experiment G-2 because it turns out the G factor for these fundamental particles is not even really exactly 2. There's something very new that comes in, and I'll come back to that in just a moment. But let me just continue with one other historical example that's easy to understand. The electron is a spin 1/2 particle, and the proton is also a spin 1/2 particle. So about the time people were understanding that the electron G factor should be 2, there was a question about what should it be for the proton? And of course, at the time, it was known that the proton was also a spin 1/2 particle with the same charge. And some very famous theorists of the day, we won't call them out, said, why would we even bother to do that experiment? We know G is going to have to be 2 because the theory is so beautiful, and we know protons are spin 1/2 particles with the same charge as the electron, although opposite. About the proton, so some good experimentalists went out and decided to determine, to do a measurement of what that G factor was for the proton. And they found it was extraordinarily different. It was like 5 point something. It wasn't even close to being 2. And the reason that is because we now know that protons are not truly fundamental particles. We know protons are actually made of stuff. They're made of 3 particles we call quarks. And in addition to those quarks, the valence quarks, there's a whole sea of other quarks and gluons that are always popping in and out of existence around the proton. And it's because of those 3 valence quarks and the sea of other stuff that's emerging around them that they're not a fundamental point particle. They still have the same charge, but now the charge is all circulating around inside a ball that has a finite size. And that leads to the proton having an extremely different magnetic moment. And so we knew that, sort of like 1930s. But it wasn't really until the 1950s that we really started to truly understand the quark nature of protons and what the true fundamental particles are that are inside the proton, and why the proton is not the same as an electron, because it's actually a composite particle made of a bunch of stuff with a bunch of charge swirling around inside of it. Okay, so now let me bring you to why the muon is cool. The muon, on the other hand, as far as we know, it's not made of anything. And we've smashed positrons and electrons together at extremely high energies at other particle accelerators, and every experiment we do basically is consistent with the notion that these are 2 point particles slamming into each other. So the way that G does start to differ from 2, though, is really cool. So it turns out every particle in the universe, as it's traveling, even through the deepest, darkest outer reaches of space, is never truly alone. As particles travel through space and time, they're surrounded continually by an entourage of other particles that are blinking in and out of existence around them. Much like that proton example I just gave, where we now know there are all these quarks and gluons that are suddenly appearing from nowhere and disappearing. That's actually true for any fundamental particle. They kind of have a cloud of these other particles that are following them wherever they go, continually blinking in and out of them.
What happens if a particle then is traveling in a vacuum, like true, like high vacuum, versus, let's say an atmosphere? I mean, in the absence of any other particles around a given particle, very few, does that promote the winking in and out of other particles out of the vacuum, or does this happen regardless of the medium in which a particle travels?
Do you struggle with concentration? Have you ever thought of your brain health long term? Bowmar Nutrition is revolutionizing the nootropic and cognitive health industry with Sharp nootropic powder and patent-pending Bright daily capsules, powered by NeuroBloom. If you struggle with focusing, think of Sharp as brain food that supports concentration. Sharp works with your natural brain chemistry to provide a heightened sense of well-being that can delay cognitive decline and also increase mood. Bowmar Sharp tastes amazing and comes in many different flavors, available in caffeinated and non-caffeinated versions. While Sharp is a short-term aid in cognitive health, think of Bright Daily Capsules as a way to improve overall brain health and prevent cognitive decline long-term. As we age, so does our brain. Supplementing with Bright has the potential to delay this aging process and helps your brain function optimally. Stay ahead of the curve and order yours today at bowmarnutrition.com and save $5 off with code GENIUS5.
Yeah, it's regardless of the medium, because the distance scale that these particles are all flipping in and out of existence is actually such a small distance scale that, whether the parent particle is traveling around and banging into an atom here or there doesn't really matter. This process goes on all the time, and it's more of a property that's intrinsic to the particle as opposed to being a part of the environment that it's in. That's a very, very good question. And so I mainly just...
quick question. Do you think the particles that wink in and out of existence, are they critical to the stability of, let's say, the magnetic moment of a proton? Like, would it not be that if it didn't have its complement of virtual particles coming in and out of existence? Are they necessary?
Well, I mean, the proton we understand pretty well, and we can actually make predictions of that magnetic moment. So we pretty well, understand that protons are complex objects that are always made of multiple particles. They always have 3 valence quarks swirling around in them, in addition to the others.
So if I'm imagining, let's say, just a proton traveling through space, and from what you're saying, it seems like there's a cloud of particles that come in and out of existence. But as they come in and out of existence, would that change the magnetic moment of a proton? Would that change any of its properties? Or does the invariance of them come from just the nature of the particle itself?
Yeah. So talking about the proton starts to get a little more complicated, because it is a composite particle made of other particles. And it's true that every one of those particles that it's made of will also have its entourage of particles blinking in and out around it. But the bulk of the reason that the magnetic moment of the proton is different from the expectation of 2 is just because of the nature of its structure, not these cloud of particles blinking out in and out of existence, although they do contribute to changing its magnetic moment at a smaller level. So that's true. But if we stick to the muons, in fact, that's why we study muons. That's why they're so valuable for the physics I'm about to describe, is because they are simpler. The physics we're trying to understand, if you tried to do it for a proton, you wouldn't be able to do the theoretical calculation of what you expect for the magnetic moment with enough precision to use the proton itself to probe for new particles, which is what we're doing with the muons. So with the muons, because they're a simple point particle, and you can in our standard model of particle physics, you can calculate how often the particles that we've discovered are blinking in and out of existence around, say, the muon. And so the idea is to go out and calculate very, very carefully, theoretically, what do you expect from the quarks, the strong sector, the gluons? What do you expect from the exchange carriers, the W and the Z bosons, the neutrinos, the Higgs boson? There's basically 17 unique particles that really form the true periodic table of the universe. And we can calculate how much each of those 17 particles should be contributing to the magnetic moment of the muon. And so the goal of our experiment is to go out and make such a precise measurement of it that not only might we see the existing 17 particles, we might see the traces of particles we haven't yet discovered. One of the big questions that I kind of reserved talking about till now was the dark matter in the universe. We look out in the universe and we see there's much more mass associated clustering around galaxies than we can explain with the visible matter, with the stars and the planets and the aliens and their spacecraft. We just can't figure out where all this additional mass is coming from. And it's not a small factor. It's like they're 5 times more massive than they should be if you tried to add up how much visible you would expect from their visible light spectrum. And we can see that this mass clumps. So we know it interacts gravitationally, but we have no idea what it is. And that's why we call it the dark matter. We believe it could be particle in nature, just like the Higgs bosons that we're swimming through all the time right now. It could be a field of particles that we're swimming through all the time that only interacts gravitationally and is therefore very, very hard to detect. Our hope is that it has a small way that it interacts with standard model particles besides gravity. And if so, it could be part of this entourage of particles that it's appearing. And so really what we're trying to do with this magnetic moment measurement is answer the question, is there an 18th particle or more than an 18th particle? Are there other new particles we haven't yet discovered in the universe that would help us explain things like the dark matter? There's an even more complicated concept. In 2013, we went out and conclusively showed that the Higgs boson was there. It sort of completed the standard model. The equations of physics for many, many decades had been pointing to the fact that a Higgs boson had to exist. In fact, we could even predict the mass that the Higgs boson should be based on other precision measurements we had made. But we finally discovered it, and it turns out it was right at the mass that we expected. But that's a puzzling value for theorists in particle physics, because naively, you would expect the Higgs to be much, much heavier. There's no reason that it should have been so light. It should have, the natural thing would have been for the Higgs to be so heavy that we wouldn't have been able to discover it at particle accelerators. But of course, we built particle accelerators to discover it because we had all this other evidence showing us that it was probably going to be light. We don't understand.
Well, quick question here about dark matter, if you would.
Yeah, sure.
When you look at, a solar system or a galaxy, and you said the matter appears to cluster, does the visible matter correlate with the dark matter? So does the dark matter sit in the same places where the visible matter is, or does it, tend to cluster differently than visible matter?
No, that's a very good question. And there's astrophysical observations we've made. For instance, one of them involves looking at the bullet cluster. And what we can tell is that the dark matter cloud is larger than the galaxy itself. So it doesn't just mimic the mass distribution of the visible matter. It's like the visible matter is more clumped at the center, and the dark matter extends out for a larger diameter around the galaxies. And we see this in multiple ways.
What does that tell you about its properties, though? That it has the different distribution. Does gravity affect it differently? Does it interact differently with gravity?
It's a good question. I'm not sure that I know the answer to that. The reason we know it clumps gravitationally because we do see it in association with these galaxies. Whether it could have a slightly different gravitational interaction, I think that's possible, but it's not my particular area of expertise. I generally know about it, but it's
no problem.
Yeah, I don't think we could rule out it having a slightly different gravitational interaction. All we know is it seems to be clumping gravitationally in some way. And we see this in a number of ways, by the way. It was first kind of observed by looking at spiral galaxies like our own Milky Way. And if you look at the rotation rates of the arms of those galaxies, they're rotating at a very different rate than you would expect based on how those arms would rotate if it was just based on the visible light we see and the density that, then tells us about how dense those arms are. That was one way, but then we've seen it in a number of other ways. We see it through a process called gravitational lensing, where we look at, and you can watch one galaxy pass behind another galaxy, and you can measure how much. It's kind of funny because, because of Einstein's relativity, we know that matter itself bends space-time. It makes little divots in the space-time continuum. And so if you have a galaxy that passes behind another galaxy, suddenly the light coming from the galaxy in the background has multiple choices of which way it can go. It can either have the shortest distance actually becomes, going to the left or going to the right. And so when we have an object that lenses, suddenly what was a point source of light will suddenly become a crescent or a circle around the mass in the foreground. And based on how much, and based on measuring how that crescent forms, you can infer how much mass must be in the galaxy in the foreground. And it's yet another way that we can tell that there's a lot of missing mass that we can't seem to account for. So this has now been shown by 2 or 3 different very independent sets of observations. And so we're very confused by the dark matter and what it might be. But,
okay, well, continuing on. Thank you for going into that.
Yeah, no problem. And the Higgs mass, which was the other thing I was going to point out, naively we expect that to be much heavier. And the easiest way to make the Higgs mass lighter is to have another set of particles interacting, again, kind of through these sort of virtual, where particles are emitted and reabsorbed sort of mechanisms. One way to bring the Higgs mass down is to have another set of particles that they're interacting with. And there's a very elegant theory called supersymmetry that would predict for every particle we've discovered so far, there's sort of a mirror particle where the spin properties are exactly opposite. So for every spin 1/2 fermion particle, we know there's a boson. Well, we don't know. The theory predicts or suggests there should be a boson. And we call those theories supersymmetric theories because it would build a new supersymmetric table where the 17 particles we have would kind of have mirror entries. It's elegant mathematically. We haven't yet found any direct evidence of it, but it's one of the most elegant ways you could figure out, you can predict why the Higgs mass is small. And it's also one of these theories where if those supersymmetric particles existed, you would expect them for sure to be appearing as part of the entourage generating the muon's magnetic moment, or at least the part of that magnetic moment that makes G differ from 2. So that's why we do it. Probably at some point want to know what we found when we ran the experiment last year. That's what
before that, what do you think this complete picture of the properties of all these particles will show you? Even if there is no 18th one, if 17's all there is, just a more complete description of all their properties, what do you think you'll see?
Well, if we run experiments and they don't find evidence of new particles or evidence of new forces, then we still have the big questions I've been discussing that we need to answer, and we have to start looking for different answers to those big questions. So maybe that answers your question. So the real problem is we have these big questions. What's the dark matter? What's the dark energy? Where did the matter in the universe go? How is the Higgs boson so light? Those questions exist no matter what. Whether or not we find the answer to them is an 18th particle or something else we haven't thought of yet. And there are other theories out there. Yeah, and there's other theories. Like some people try to build modifications to gravity that would provide a gravitational model that could explain these mass measurements of galaxies without needing to invoke a cloud of particles surrounding them. But they're starting to become pretty heavily disfavored because they can't seem to explain all of the evidence that we've now gathered. So, but
is there a force described of the interaction of the? So first of all, what do you call the particles that wink in and out of existence? The cloud around a given particle. Is there a name for that?
Sometimes people refer to that as the quantum foam. Of course, as I mentioned earlier, those particles are just the 17th. Particles we know about. And so because of the theory of quantum electrodynamics, we know that electrons and photons are constantly popping in and out of existence. Because of understanding the strong force, we know quarks and gluons are always popping in and out of existence around the muon. Because of electroweak, we know W and Z bosons and neutrinos. So that entourage of particles, we know for sure the existing particles are doing that. And that's why when we go out to determine the G factor of the muon, many decimal places in that the calculation are already known by the.
So what I'm saying is, do the fundamental forces explain also the interaction of one particle's quantum foam with another particle's quantum foam, for lack of a better term, whereas their interaction of their two entourages lead to the arising of other forces?
Those particles that appear and disappear are really just the standard particles, and they appear because of the standard forces we know about. Along with like Heisenberg's uncertainty principle that allows us to violate things like conservation of energy for a very short amount of time. That's what enables them to even blink in and out of existence, is the fact that the universe is fuzzy at that level. But once they appear, they just have the same properties that the particle that's just propagating through space all the time has. It's just they don't get to exist very long once they pop into existence. They're kind of cheating the world by violating conservation of energy, so they can only do that for a very short amount of time.
Okay, gotcha. So again, what's the utility of figuring out your project in particular, Muon G-2?
Yeah, the utility in it is really comes back to the mission of the laboratory itself that I mentioned earlier. Our goal is to really study the fundamental forces, the matter that the universe is made out of at its most basic level, and how that interaction happens as things propagate through space and time. The reason we do it, we had our famous first director was asked a very similar question by Congress. Why should we fund this endeavor? And he has a beautiful statement. I should just read it to you, but I can paraphrase it, where he said, the reason we pursue this kind of science is really for the same reason we pursue art and we pursue music, and we spend a lot of resources on things that otherwise you would say, what is the purpose of that? The purpose of that is that humans have a natural curiosity, and we're driven to understand this beautiful world we live in and make beautiful things. And so that is really the outcome. That is really what we're looking for when we do experiments like this. Is trying to really understand the basics, just for the simple reason of wanting to expand humanity's knowledge. And, once you know about one of these fundamental interactions or these fundamental forces, then you quite often will figure out, spin-offs and, things that will come from that better understanding. But that's not the primary reason we do it. We also produce a lot of technological spin-offs. For instance, the World Wide Web was started at our sister laboratory, CERN, in Europe. And a lot of the magnet technology that you see around today, the MRI magnets that have been such a huge contribution to the medical world and doing our medical imaging, those were developed because we developed these high field magnets in the realm of trying to build better particle physics accelerators that enabled us to really have MRI magnets that are used everywhere for applications now. PET scanners, all the detector technology that we use for PET scanners, positron emission tomography, all those detectors essentially started as particle physics detectors that then found their way into medical applications. So, we do a lot of great things for society, but our fundamental reason we exist is to really just try and understand the universe to satisfy humankind's curiosity.
Well, very good. Where can people find out more about Fermilab? Just go to the lab website, or is there a place?
Oh, okay, yeah. So let me just mention real quick why this result was so interesting. So this was a result that was published last April. The first result from this experiment. It was, this experiment was 10 years in the making. By the time you design it, you get it funded, you construct it, you take the data, you analyze the data. And we finally, after 10 years, a team of 200 scientists working on it. These scientists are graduate students, postdocs, professors, national laboratory scientists. After 10 years of putting it together, we finally released the first result last year. And what we found is that the value we see experimentally is only consistent with what you would expect from the known particles at about a 1 in 40,000 probability. So if you did the experiment 40,000 times, you might get a result as weird as the one we got. And so that's starting to look extremely unlikely. Like there must be new particles that are contributing to this quantum foam. And so the way we, determine eventually what those are has to do with working with theoreticians that go out and take various models for what that new physics can be. And then they try to predict if they can see the same level of deviation that we see in our measurement. And so that's what's come out. There's been some interesting developments since then also. Part of that calculation requires knowing how often quarks are emerging in that part of that entourage. And that's a very difficult calculation to do. You can't do it from first principles with a pen and a piece of paper. You can't do it through what we call perturbative calculations because it's just a calculation that you can't do with the various tricks we have for doing analytical calculations. So what we do instead is we go to our atom smasher friends who collide particles, and we ask them to just determine for us, when you collide a positron and electron together, how often do you see quarks that come out? So that way, rather than having to rely on a theoretical calculation, we just compare it to a data-driven calculation of how often that happens. And that's how we construct the theory for which we compare our experiment. The thing that's become very interesting in the last 10 years is that there has been an attempt to take all of this kind of physics involving quarks and gluons and be able to do calculations on the world's greatest supercomputers. Supercomputers have gotten to the point that you can start to think about, even if you can't do these calculations analytically, you can just let a computer simulation tell you the answer. And that computing is called lattice quantum chromodynamics. That's the technical name for it, because it's calculating the QCD forces on a computer, on a lattice, on a grid that mimics them in space. And some of those computer programs are now starting to tell us that maybe the answer here is that we're getting more quarks and gluons than we expect. And so if that's the case, then that's probably the less exciting of the answers that would help explain it. But that's an area that's still under development, and we'll see what they have to say. In the meantime, the data we published last year was about, maybe a 16th to a 20th of what we will eventually publish. It was our very first result from our first year of data taking. So experimentally, we're going to improve our knowledge pretty dramatically over the next 2 or 3 years. And in the meantime, we'll see how the theory works out. This is the handshake we always have. So,
well, very good. And again, for people that want to follow up and learn more, where can they go?
The best place to go would be just to type Muon G-2 into your web browser, and you'll find links to Fermilab and our experiment. It's a unique enough name. You just spell that MUON space the letter G and then the minus sign and the number 2. Otherwise, you can just go to the Fermilab. You can just type Fermilab also, and you'll find it through the links at Fermilab.
Well, very good. Well, thank you for coming on the podcast. I appreciate it.
Hey, thank you, Richard. I appreciate you giving us a chance to talk about the great science we do.
Do you struggle with concentration? Have you ever thought of your brain health long term? Bowmar Nutrition is revolutionizing the nootropic and cognitive health industry with Sharp nootropic powder and patent-pending Bright daily capsules, powered by NeuroBloom. If you struggle with focusing, think of Sharp as brain food that supports concentration. Sharp works with your natural brain chemistry to provide a heightened sense of well-being that can delay cognitive decline and also increase mood. Bowmar Sharp tastes amazing and comes in many different flavors, available in caffeinated and non-caffeinated versions. While Sharp is a short-term aid in cognitive health, think of Bright daily capsules as a way to improve overall brain health and prevent cognitive decline long-term. As we age, so does our brain. Supplementing with Bright has the potential to delay this aging process and helps your brain function optimally. Stay ahead of the curve and order yours today at bowmarnutrition.com and save $5 off with code GENIUS5.
You've been listening to the Finding Genius podcast with Richard Jacobs. If you like what you hear, be sure to review and subscribe to the Finding Genius podcast on iTunes or wherever you listen to podcasts. And want to be smarter than everybody else? Become a premium member at findinggeniuspodcast.com. This podcast is for information only. No advice of any kind is being given. Any action you take or don't take as a result of listening is your sole responsibility. Consult professionals when advice is needed.